NAV, also known as the Network of Autonomous Vehicles, is a system in which automated or driverless vehicles can send and receive data in order to improve road safety and traffic flow. NAV uses available wireless infrastructure and protocols to relay critical data from vehicle to vehicle and coordinates traffic movements via a central control server. While autonomous driving technology is available in many new cars today, the issue of poor vehicle-to-vehicle communication remains. This can cause dangerous situations or even traffic accidents due to misinterpretations by drivers or systems. The national average for vehicle collisions according to the ENOS Center for Transportation is nearly 6 million per year. By combining autonomous driving technology and a comprehensive live data sharing network, this would reduce traffic collisions by 4 million in 3 years. As engineering students, we have developed a proof of concept using off-the-shelf controllers and sensors that demonstrate the benefits of using NAV's network. By purchasing a baseline kit from SunFounder and augmenting the design with our own sensors, circuits, and autonomous logic, we were able to develop 3 small-scale autonomous vehicles for demonstration purposes. There are 4 primary devices on each car. The Raspberry Pi 3, programmed in Python, handles all inputs and outputs. The motor driver provides power to the 6-volt motors. The DC buck converter takes power from the lithium-ion batteries and converts it to 5 volts DC, and the servo driver controls the pulse width to both the steering servo and the motor controller. The external components to these devices are the 6-volt DC motors which drive the back wheels, the SG Mini servo which directs the steering, the infrared line sensors which read light versus dark colors, the infrared object avoidance sensors which detect obstructions, the ultrasonic sensor which determines object distance, and the RFID scanner reads RFID tags underneath each lane and determines location based upon each card read. The combination of these sensors and controllers allows the autonomous vehicles to navigate their environment effectively. It should be noted that due to the fact that we used infrared sensors in our prototype cars, sunlight can cause interference and result in poor performing vehicles. The components of the network hardware consist of a 5 dB wireless router and a Raspberry Pi acting as the control server. These components produce a wireless network that each car connects to automatically with their integrated wireless antennas. Our network uses a star topology which allows vehicle hosts to enter and leave the network without disrupting the network integrity. A central control server interprets and forwards incoming data to the appropriate cars given the data information and car's registered location. Given our scale, our prototype uses 2.4 GHz wireless technology and TCP/IP as baseline network protocol. To minimize interference from other wireless networks, we monitor channel utilization using a wireless analyzer called Wi-Fi Analyzer. You might be asking yourself, why do we need a network? Can't autonomous vehicles drive themselves? What if a car's sensor malfunctions? In this example, the car on the right has left-sized sensors which have malfunctioned. With the network as a backup, that car can verify that the other car is still present. Since the car on the left will see the car on the right, the car on the right can interpret the network data and determine that the obstruction is in fact itself. This is similar to a person who is blind being led by those who can see. With the use of a multi-threaded socket, the server can handle communication with multiple clients. Information such as vehicle location, peripheral sensor data, stop condition, and lane merging state are all sent from each car to the central control server. Each car's vicinity to other cars is determined by RFID track locations which act as position markers. The track contains 16 separate zones with 8 zones per lane. The server then determines location relevance and based upon each vehicle's registered location, forwards any critical sensor or command data to the corresponding cars. Vehicles that are adjacent will receive sensor data regarding one another, whilst vehicles outside of this range will only receive commands from the server. For instance, in this example, each car has its own perspective. Car 2 will only share information with cars 1 and 3 and vice versa. Since cars 1 and 3 are not adjacent, they will not share information with one another. The following example shows the data being shared when a car has a stop condition symbolizing a traffic incident. Since car 1 has stopped and is in the outer lane, the server has sent out a command to all cars in car 1's lane to merge right. It should be noted that based on a car's location, that car knows whether or not it can merge right. The following example demonstrates the ability of the network to provide a backup for blind spot detection. Car 3 is on the left side of car 1, demonstrated by car 1's left sensor seeing car 3, and car 3's sensors seeing car 1. Each car also has predetermined procedures based upon data read by its own sensors and received from the network. For instance, in this particular case, car 1 has a forward overlap over car 2, and car 2 wants to merge into car 1's lane. The obstructed merge protocol will cause car 1 to speed up, while at the same time car 2 will slow down. Once both cars are clear of one another, car 2 can merge left into car 1's lane. Even though car 1 could not see car 2 in this example, this coordination relies upon the NAV network to share sensor, position, and merge state information with car 1. In this second example, both cars are equally overlapped. Since car 2 wishes to merge into car 1's lane, the protocol dictates that car 2 slow down and car 1 maintain its normal speed. Since car 1 is in the outer lane, its speed is higher than car 2, which is in the inner lane. Once the cars are clear of one another, car 2 can merge into car 1's lane. There is also a particular case where any car that is stopped will cause all cars in that particular lane to merge into the opposing lane and avoid the stopped car. This procedure is also useful for cars which may be slower than cars behind them. When a faster car comes up to a slower car, and this causes the faster car to slow or stop, the slower car will receive a merge command and merge into the opposing lane to give way to the faster car.